3I Atlas should have been a surprise. Interstellar objects arrive randomly, unpredictably from the darkness between stars, except leaked files reveal a surveillance network that was waiting for it. Not searching, waiting. The leaked imagery carries metadata signatures matching Defense Department classifications. The sensor platforms match descriptions from a paper published in 2005 called Cassandra. Same technology, same positions, same capabilities, built over 20 years to detect something that was officially discovered in 2025. Tonight, we're walking through the evidence that suggests 3I Atlas wasn't discovered. It was intercepted. Stay with me. Because by the end, you'll see why some observers believe this object was expected, tracked and studied long before the public ever heard its name. If you're as captivated by this mystery as I am, go ahead and like this video and subscribe so you stay connected as this story continues to develop. Leave a comment telling us your location, your current time, and whether you think the complete story about 3I Atlas is actually being shared with the public. Part 1. The leak that rewrites the timeline. Something arrived in an online forum on November 2nd, 2025. It wasn't supposed to be there. A private group of amateur astronomers and satellite trackers, the kind of people who spend their nights watching for classified launches and decoding orbital debris, suddenly had access to something that didn't belong in civilian hands. High-resolution imagery, multi-spectrum captures, tracking overlays with classifications that made people go quiet. The files showed an object, officially designated 3I/Atlas, an interstellar comet that had just passed its closest approach to the Sun 4 days earlier. But these weren't amateur telescope snapshots. These were military-grade surveillance files. The leaked packet contained 3 distinct datasets. First, imagery labelled Oracle Ge, showing the object in extraordinary detail from a vantage point that shouldn't exist in public records. Second, something called Argus Vis multispectrum captures, revealing the comet across wavelengths invisible to standard observatories. Third, and most disturbing, overlays from a system identified only as Cassandra, displaying tracking vectors and trajectory predictions with the kind of precision you'd expect from missile defense networks, not asteroid surveys. The metadata embedded in these files had a signature. Anyone who'd seen previous Defense Department leaks recognized it immediately. The font choices, the file naming prefixes with specific alphanumeric sequences, the checksum formatting. This had the fingerprints of classified defense architecture all over it. One image in particular stopped people cold. A black and white frame showing 3I Atlas surrounded by what appeared to be structured emissions. Not the chaotic spray of gas and dust you'd expect from a comet, but organised almost geometric patterns. 4 plasma streams extending from the nucleus in cardinal directions, bright green against the darkness, perfectly symmetrical. Comets don't do that. Comets tumble and spew and fragment. They're messy. This looked designed. The timing of the leak matters more than you might think. Just days before these files appeared, new observations from Hubble and the European Space Agency's ground telescopes had shown something unexpected. 3I Atlas was brightening. Not gradually, like a comet heating up as it approaches the Sun, but in discrete jumps. Sudden increases in luminosity that didn't correlate with its distance from the Sun or any known outgassing mechanism. The scientific community was already puzzled. Then these leaks dropped, and the puzzle became something else entirely. Here's where the story stops making sense. 3I Atlas was officially discovered in 2025. The public announcement came in late October, describing it as a newly detected interstellar visitor, only the 3rd confirmed object to enter our solar system from beyond. But the leaked files revealed a surveillance infrastructure that couldn't have been assembled in weeks. Oracle 6 imagery from a satellite platform at Earth-Moon Lagrange Point 1. Argus Vis sensors with capabilities suggesting decades of development. A tracking database called Cassandra, with exabyte-scale data ingestion architecture. You don't build that kind of system overnight. You don't even build it in a few years. This creates what some observers are calling the timing paradox. If 3I Atlas was discovered in 2025, why did a comprehensive, multi-layered surveillance network already exist to track it? Why was the infrastructure in place before the discovery? The official narrative describes 3I Atlas as just another interstellar comet. Unusual, perhaps, but fundamentally a natural object following physics we understand. The leaked files suggest a very different story. They suggest someone knew it was coming. The public reaction split immediately into predictable camps. Skeptics called it an elaborate hoax, pointing out that anyone with Photoshop skills could fabricate metadata and slap classified-looking labels on telescope images. Believers saw confirmation of long-suspected secret space programs, government cover-ups, perhaps something more extraordinary. What matters isn't which camp you fall into. What matters is asking the right questions. And the central question, the one that makes this story worth investigating, is simple but profound. Why does the architecture revealed in these leaks suggest that 3i Atlas was expected for 20 years? That number isn't random speculation. It comes from a document that shouldn't exist, or more accurately, a document that shouldn't be relevant. A paper presented at an academic conference in 2005, 20 years before 3i Atlas appeared. A paper that describes, in unsettling detail, a planetary defense system nearly identical to what these leaks revealed. Not similar, not inspired by the same general ideas, identical. Down to the specific technologies, the orbital positioning, even the names of the systems involved. The paper was titled Cassandra. Part 2, Cassandra, the academic paper that shouldn't exist. 20 years ago, at the International Astronautical Congress in Valencia, Spain, a group of researchers presented a paper that nobody paid much attention to. The title was dry, academic, forgettable. IAC 06-3.5.07. The subtitle was more descriptive, but still bland enough to fade into the background noise of conference proceedings. Cassandra, a strategy to protect our planet from near-Earth objects. Planetary defense papers were common. Asteroid detection, deflection strategies, early warning systems. Everyone agreed we needed better ways to spot dangerous space rocks. This paper should have been one of dozens making similar arguments, except Cassandra wasn't making general arguments. It was describing a specific, detailed architecture, a blueprint for a surveillance network that wouldn't make sense for asteroid defense but would make perfect sense for something else entirely. The paper proposed positioning what it called an Oracle-class platform at the Earth-Moon Lagrange 1 point. Not in low Earth orbit, where most satellites operate, not in geostationary orbit, where communication satellites park. At L1, a gravitationally stable point between Earth and the Moon, 60,000 kilometers above Earth's surface. The paper explained this positioning would allow continuous observation of the region between Earth and the Sun, with the added benefit of being able to use the Sun as a backlight to detect faint, distant objects. 21 years later, the leaked files reference a system called Oracle ZIGS, operating from precisely that location. The Roman numeral 6 suggests there were 5 predecessors. The designation EML1 appears in the file metadata. Earth-Moon Lagrange 1, exactly what Cassandra proposed. The paper went further. It described a multi-spectrum imaging array capable of capturing objects across visible, infrared, ultraviolet and X-ray wavelengths simultaneously. The stated purpose was detecting small asteroids with low albedo, space rocks too dark to spot easily against the background of space. But the specifications went far beyond what you'd need for asteroid hunting. The proposed system would incorporate what the paper called hyperspectral analysis modes, allowing detection of specific chemical signatures at extreme distances. It would track multiple objects simultaneously using an array of independent imaging streams. The paper even included preliminary diagrams of the sensor geometry, showing how dozens of individual telescopic elements could be coordinated to provide continuous coverage. The leaked Argus Vis system matches this description with uncomfortable precision. The name itself is telling. Argus, from Greek mythology, the giant with 100 eyes. Vis, from Latin, meaning sight or vision. The original DARPA Argus is surveillance platform, developed in the early 2000s, used 1.8 gigapixels and could track targets across entire cities simultaneously. The leaked files suggest Argus Vis operates with 256 simultaneous video streams and hyperspectral capabilities. That's not an incremental upgrade. That's a complete reimagining of what surveillance from space can accomplish. Then there's the database architecture. Cassandra proposed what it called a distributed fault-tolerant exabyte-scale ingestion engine for storing and processing detection data. This was in 2005, remember, when the term big data was just entering popular usage. The paper described a system that could handle continuous data streams from multiple sensors, process them in real time, identify anomalies, and maintain complete historical records stretching back decades. The technical specifications read like a preview of modern distributed computing systems. More specifically, they read exactly like Apache Cassandra, the open-source database platform released in 2008 and now used by major tech companies for managing massive datasets. You might think this is coincidence. Maybe the database was named after the paper, or maybe both were named after the mythological prophet Cassandra, cursed to utter true prophecies that nobody would believe. But here's what makes it strange. Apache Cassandra was developed at Facebook, later released as open source, and became the foundation for data systems handling petabytes of information. The Cassandra paper predated this by 3 years and described nearly identical architecture. Either the paper's authors were remarkably prescient about database technology, or they were describing something that already existed in classified form. The academic tone of the paper makes everything more unsettling. It reads like a typical conference presentation, full of citations, theoretical frameworks, mathematical models. But buried in the technical jargon are details that don't quite fit. The paper discusses detection of objects at cosmic background noise levels, meaning objects so faint they're almost indistinguishable from the random photons filling space. Why would you need that sensitivity for asteroids? Even small near-Earth objects are relatively bright compared to interstellar space. You'd only need background-level detection if you were looking for something coming from outside the solar system, something arriving from the darkness between stars. Several of the paper's co-authors had interesting backgrounds. Not astronomers or planetary scientists, but engineers who'd worked on missile tracking systems. Ballistic missile defense requires detecting small, fast-moving objects against the backdrop of space, discriminating real threats from decoys, and maintaining tracking locks through atmospheric interference. Those skills don't obviously translate to asteroid detection, but they'd be perfect for tracking something like 3i Atlas, an object moving faster than anything bound to our Sun, following a trajectory that doesn't quite match gravitational predictions, surrounded by a plasma envelope that might interfere with normal detection methods. The benign interpretation is straightforward. The authors were simply ahead of their time, proposing technologies that wouldn't be feasible for years, but that represented genuine innovation in planetary defense thinking. Conferences exist to share forward-looking ideas. Maybe Cassandra was just exceptionally visionary. The darker interpretation is harder to dismiss. What if Cassandra wasn't predicting? What if it was preparing? What if a small group of researchers with access to classified intelligence knew something was coming, knew roughly when it would arrive, and published an academic paper as a way to lay the groundwork for technologies that would need public explanation eventually? You can't suddenly reveal a massive space surveillance network without raising questions about when and why it was built. But if there's a paper trail showing that smart people proposed this kind of system decades earlier, it provides plausible cover. Of course we built this, see? Researchers suggested it years ago. The Cassandra paper received no significant public follow-up. It wasn't cited extensively. No major space agencies announced programs based on its recommendations. It should have disappeared into the vast archive of conference proceedings that nobody ever reads again. Until November 2nd, 2025, when leaked files revealed that every single technology Cassandra proposed was apparently operational and had captured an interstellar object behaving exactly as the paper had theoretically predicted. If Cassandra laid the foundation, Oracle 6 is the smoking gun. Part 3, Oracle 6, the Del-1, the satellite, hiding in plain sight. Let me tell you about a place in space that most people don't know exists. 60,000 kilometers above Earth, along the line connecting our planet to the Moon, there's a point where gravitational forces balance perfectly. It's called the Earth-Moon Lagrange 1 point, or L1 for short. Objects placed there don't need much fuel to maintain position. They just hang there, held in place by the delicate equilibrium between Earth's gravity pulling one way and the Moon's gravity pulling the other. It's an ideal spot for a satellite you want to keep in one place for a long time. It's also an ideal spot for a satellite you don't want people asking too many questions about. The leaked files labelled their imagery with a designation that appeared at the top of every frame, Oracle SIR-EML1. That's not subtle. That's a system identifier stating exactly where the platform is located and what it's called. The Roman numeral 6 implies a series, a progression of designs or deployments. Oracle 1 through 5 came before. Maybe they were prototypes, maybe they failed, maybe they're still up there, doing things we don't know about. Oracle 6 is the version that allegedly captured Three-Eye Atlas during its approach. From L1, you have an unobstructed view of the space between Earth and the Sun. This region, called the inner solar system or sometimes the danger zone, is where most near-Earth objects approach from. Asteroids, comets, anything on a trajectory that might threaten Earth usually comes from this direction. But there's another advantage to L1 that the Cassandra paper emphasized. You can use the Sun as a backlight. When an object passes between your sensor and the Sun, it creates a silhouette, a shadow that's often easier to detect than trying to spot reflected sunlight off a dark, distant rock. This technique is called transit detection, and it's incredibly powerful for finding faint objects. Solar observatory logs from missions like SOHO and Dieskova, satellites that actually operate near L1, contain something interesting if you know what to look for. Occasional occlusion shadows that don't match any documented spacecraft. Brief moments where instruments detect something blocking a tiny fraction of their view, something that wasn't supposed to be there. These anomalies appear sporadically in the public data. They're usually dismissed as instrument glitches, cosmic ray hits, or passing debris. But if you plot their timing against significant astronomical events, particularly the perihelion passages of long-period comets, you notice correlations. The shadows appear when something unusual is happening, as if another craft at L1 is repositioning, adjusting its orientation, preparing to capture data during a brief observational window. In 2022, the Air Force Research Laboratory awarded a contract for something called Oracle P. The public documentation described it as a next-generation space surveillance platform, scheduled for launch in 2026. The stated purpose was tracking satellites and debris into lunar space, the region between Earth and the Moon. Perfectly reasonable. Space is getting crowded. We need better tracking. But the specifications included in the unclassified portions of the contract mention capabilities that seemed excessive for satellite tracking. Multi-spectrum imaging across 12 wavelengths, detection thresholds calibrated for objects at lunar distance and beyond, data processing architecture designed to handle continuous high-resolution feeds from multiple sensor arrays simultaneously. The leaked files imply two possibilities. Either Oracle 6 is a classified predecessor to Oracle P, deployed years before the public version was even announced, or Oracle P was always meant to be the unclassified cover story for systems already operational. You tell the public you're building something, show them contracts and press releases, but what you're actually building is the 7th or 8th iteration of a platform that's been watching the skies for longer than anyone admits. Why would you need a satellite at L1 capable of detecting weak signatures from beyond the heliopause? That's the boundary of our solar system, where the sun's influence fades and interstellar space begins. It's billions of kilometers away. Nothing we currently track comes from that far out, except objects like Three-Eye Atlas, except interstellar visitors that spent millions of years crossing the void between stars before entering our cosmic neighborhood. If you knew such an object was coming, if you had advance warning measured in years or decades, you'd want a sensor position to catch it as early as possible. You'd want continuous monitoring during its approach. You'd want every spectrum, every wavelength, every piece of data you could extract. Aerospace insider forums, the kind where retired engineers and industry veterans discuss things they probably shouldn't, have mentioned a non-SOHO L1 resident craft for years. These discussions are vague, carefully worded, never confirming anything specific. But the pattern exists. People who worked on space surveillance programs talking around the edges of something they can't directly acknowledge. A platform that isn't officially there, but that everyone in certain circles knows about. Let me be clear about what's verified versus what's speculation. Verified facts include the existence of the Oracle P contract, the public documentation of L1 as an orbital position with specific advantages for space surveillance, and the basic orbital mechanics that make everything in the Cassandra paper technically feasible. What's speculative is the claim that Oracle 6 tracked Three-Eye Atlas before its official discovery. We have leaked files suggesting this happened. We don't have independent confirmation. The files could be fabricated. The entire leak could be disinformation. But if it's real, it means someone watched Three-Eye Atlas coming for months or years, tracking its approach with instruments the public didn't know existed, waiting for it to arrive. Three-Eye Atlas exhibited unexpected brightening during its approach. Not the gradual increase you'd predict as a comet gets closer to the sun, but sudden jumps in luminosity that appeared almost like switches being flipped. These brightness events didn't correlate with the object's distance from the sun or its orientation. They seemed independent of normal cometary physics. From an L1 vantage point with multi-spectrum sensors and continuous coverage, you'd see those events in exquisite detail. You'd capture the exact moments when the brightness changed, the wavelengths involved, the geometric patterns in the plasma envelope surrounding the nucleus. Oracles didn't just observe 3i Atlas. If the leaks are accurate, it was positioned and calibrated specifically to capture an object matching 3i Atlas's profile. That's not an accident, that's preparation. But the platform that actually produces the imagery, the eye at the end of the telescope, is even more remarkable. Part 4, Argus Vis, the eye built for an unknown visitor. Imagine you're designing a surveillance satellite. Your goal is to track objects moving through space, potentially moving fast, potentially changing velocity or direction, in ways you can't predict. You need to see them across multiple wavelengths because different materials reflect or emit different colours of light. You need to track many objects simultaneously because you might not know which one matters until it does something unexpected. You need enough resolution to distinguish between a rock and something else, between chaos and structure. What you're describing is Argus Vis, or at least what the leaked files claim Argus Vis can do. The original DARPA Argus IS platform, developed in the mid-2000s and deployed on high-altitude drones, was a revolution in surveillance technology. 1.8 gigapixels of resolution, 130 independent video streams processed simultaneously. The system could watch an entire city at once, tracking every vehicle, following every person, reconstructing events from multiple angles. It was designed for battlefield awareness, giving military commanders a god's-eye view of complex operational environments. The technology demonstration videos showed cars being followed across miles of urban terrain, individuals tracked through crowds, patterns of movement analysed in real time. Argus Vis appears to be what happens when you take that concept and push it into deep space. The leaked files reference 256 simultaneous video streams. That's not an incremental improvement. That's doubling the capability multiple times over. More importantly, the specifications mention hyperspectral imaging, meaning the system doesn't just see invisible light but across dozens of narrow wavelength bands. Every stream captures a different slice of the electromagnetic spectrum. Visible red, infrared, ultraviolet, specific emission lines for elements like sodium, cyanogen, ionized oxygen. You can identify what an object is made of from the light it emits or reflects. The system allegedly performs rotational sweeps, constantly adjusting its orientation to maintain tracking locks on multiple targets, even as they move relative to the platform's position. This is gross overkill for ordinary asteroid or comet observation. Those objects follow predictable trajectories. You point your telescope, take your measurements, and move on. You don't need dozens of simultaneous video feeds. You don't need hyperspectral analysis of every emission line. Unless you're tracking something that might not behave predictably. Unless you're watching for changes that happen fast, changes that might indicate non-standard physics. 3i Atlas exhibits non-gravitational acceleration. That's the technical term for when an object doesn't move exactly the way gravity alone would make it move. Comets show this all the time because outgassing creates tiny rocket effects, pushing them slightly off their predicted paths. But the magnitude and direction of 3i Atlas's acceleration don't match normal comet behaviour. The force vector doesn't align with the Sun. It's not symmetric around the nucleus. It appears, from the data we have, to vary in ways that suggest something other than random gas jets. The Cassandra paper predicted this. In a section discussing potential characteristics of interstellar objects, it mentioned the possibility of phase events involving structured emissions. The paper didn't say alien spacecraft. It didn't say artificial intelligence or probes. It used careful, scientific language about objects that might interact with solar radiation or magnetic fields in non-standard ways, creating emission patterns that would appear geometric or organised. It suggested such objects might require specialised tracking because their behaviour couldn't be predicted using standard celestial mechanics alone. Argus Vis was apparently built to capture exactly that kind of behaviour. The recent brightness fluctuations of 3i Atlas, those sudden jumps in luminosity, would be visible across Argus Vis's multiple wavelength channels simultaneously. You'd see which specific emission lines were brightening. You'd correlate the brightness changes with the object's rotation, its position relative to the Sun, any changes in its plasma envelope. You'd build a complete picture of what's happening in a way that ground-based observatories, even major facilities like the Hubble Space Telescope, simply cannot match. Structured emissions are the most troubling aspect of the leaked imagery. Normal comets produce chaotic outgassing. The nucleus heats up, subsurface ice vaporizes, gas bursts through cracks in unpredictable directions. You get jets and plumes, but they're irregular, asymmetric, influenced by the comet's rotation and internal structure. 3i Atlas, in the leaked images, shows cardinal plasma jets. 4 streams extending from the nucleus at roughly 90-degree intervals, stable over time, bright green against the black background. The colour indicates ionized cyanogen, a molecule common in comets but not usually concentrated in such defined patterns. Geometric patterning in space isn't necessarily artificial. Nature creates hexagons in Saturn's North Pole jet stream. Ice crystals form perfect 6-sided snowflakes. Magnetic fields organise plasma into loops and arcs. But random natural processes rarely produce fourfold symmetry. That pattern suggests either an extremely unusual natural phenomenon we don't yet understand or something else. Argus Vis could resolve microvariations in the coma shape, the cloud of gas and dust surrounding the comet's nucleus, at scales impossible from ground-based observation. Even the most powerful Earth-based telescopes are limited by atmospheric turbulence, by the sheer distance to the object, by the need to share observing time between multiple research programs. A dedicated platform at L1 faces none of those constraints. It watches continuously. It never blinks. Every subtle change, every fluctuation, every moment when the object does something unexpected gets captured in exquisite, multi-spectral detail. None of this proves artificiality. That's important to emphasize. Unusual doesn't mean impossible. Strange doesn't mean designed. The universe is full of phenomena that seem impossible until we understand the physics. Ball lightning, fast radio bursts, neutron star glitches, they all seemed impossible once. But the fit between what Cassandra predicted 20 years ago and what Argus Vis allegedly captured is unsettling. It's like someone wrote a script for a movie, filed it away, and then watched. Reality followed that script exactly. If Cassandra predicted this behaviour and Argus Vis captured it, the question becomes unavoidable. Why was there silence for 20 years? If researchers knew enough in 2005 to design this system, knew enough to predict objects exhibiting these exact characteristics, why didn't they say anything? Why let 2 decades pass without follow-up papers, without public discussion, without preparing the scientific community for what might be coming? The silence itself is data. It's a clue. Part 5. The 20-year silence, and why it's breaking now. Let me walk you through a timeline that doesn't make sense unless you assume something unusual has been happening behind closed doors. We start in 2005 with the Cassandra paper, presented at an academic conference and then largely forgotten. The paper gets filed in conference proceedings, may be referenced by a handful of researchers working on tangential topics, but generates no significant follow-up. No major space agency announces initiatives based on its recommendations. No follow-up papers from the original authors. It just sits there, a blueprint gathering digital dust. Jump forward to 2012. A subtle funding anomaly appears in Department of Defense budget documents. The line item is vague, labelled as Space Situational Awareness Enhancement, allocated just under the threshold that would require detailed congressional reporting. This kind of thing happens all the time in defense budgets. Projects get funded through obscure channels, capabilities get developed without public announcement, and we usually only learn about them years later when they're declassified, or when someone leaks information. But the amount and timing of this particular allocation is interesting if you're looking for it. Move to 2016, another spike in black budget spending, this time explicitly connected to deep space imaging. The unclassified portion of the budget summary mentions advancing capabilities for detecting objects beyond lunar orbit, improving sensor sensitivity for faint targets, and developing data fusion techniques for combining information from multiple platforms. These are reasonable, justifiable expenses. Nobody questions them. But the classified portion of that budget, the actual dollar amounts and specific programs, remains hidden. Fast forward to 2024. Several individuals with backgrounds in aerospace and intelligence begin making vague references to a long-running program focused on interstellar surveillance. These aren't prominent whistleblowers holding press conferences. These are careful, cryptic mentions in podcasts, forum posts, comments that could be dismissed as speculation but that share consistent themes. Someone is watching the space beyond the heliopause. Someone has been watching for years. Something is expected. Then 3i Atlas appears in 2025, and, within days of its perihelion passage, the leaks arrive, not before perihelion, after. That timing is critical. A leaker needs leverage, needs proof that their claims are accurate. Releasing surveillance files before the object's closest approach would be premature. Skeptics could argue the imagery was fabricated, the predictions wrong, the entire story a hoax. But releasing the files after perihelion, when the object has survived its pass by the Sun, when its unusual behaviour is becoming apparent to professional astronomers, when ground-based observations are starting to confirm that something strange is happening, that's when the leak has maximum credibility. Rational motives for maintaining secrecy over 20 years are easy to construct. National security considerations would top the list. If you've developed advanced space surveillance capabilities that exceed anything your adversaries possess, you don't advertise that advantage. You keep it quiet. You use it to monitor foreign satellites, track missile launches, maintain an edge in what military strategists call the ultimate high ground. Revealing the existence of systems like Oracle 6 and Argus Vis would invite countermeasures, would encourage rival nations to develop their own systems, would trigger an arms race in deep space monitoring that nobody wants. Avoiding public panic is another plausible motive. Imagine the reaction if the government announced in 2005 or 2010 that an interstellar object would arrive in approximately 2025, and that this object might exhibit characteristics inconsistent with natural phenomena. The response would range from dismissal to hysteria. Scientists would demand evidence. Conspiracy theorists would claim vindication. Religious groups might see apocalyptic implications. The societal disruption could outweigh any benefit from early disclosure. There's also the geopolitical dimension. Space is becoming militarized whether we acknowledge it or not. China and Russia are developing anti-satellite weapons, orbital interceptors, capabilities that could threaten American space infrastructure. If the United States possesses surveillance technology that can track objects at interstellar distances with precision sufficient to characterize their composition and behavior, that's a strategic asset. It has implications beyond astronomy. It demonstrates technological prowess that translates into terrestrial power. But let me offer a more speculative motive, one that fits the pattern of evidence we're examining. What if Cassandra wasn't about asteroids at all? What if the entire planetary defense framing was cover for a program designed to repair for a specific event? What if some group within the defense and intelligence establishment had information, whether from extrapolation of early observations, mathematical models, or something else entirely, suggesting that an object matching 3i Atlas's parameters would arrive around 2025? This interpretation sounds paranoid until you consider what it would take to predict an interstellar arrival. Objects travelling between stars move at velocities that require millions of years to cross galactic distances. If you detect something at the heliopause, the boundary of our solar system, you have at most a few years of warning before it arrives in the inner solar system. That's not enough time to design, build, launch, and deploy the kind of comprehensive surveillance network the leaks reveal. You'd need decades of lead time. You'd need to start preparing long before the object was detectable through conventional means. The only way that works is if you had advance warning through non-conventional means. Theoretical predictions based on interstellar object arrival rates would be too imprecise. You'd get probabilities, rough estimates, nothing specific enough to justify a 20-year classified program, unless someone calculated something else, unless there was a pattern, a cycle, a reason to expect objects like 3i Atlas at predictable intervals. The leak happening after perihelion suggests the leaker needed proof. They needed to demonstrate that the object survived solar approach, that it behaved as predicted, that the surveillance infrastructure worked as designed. Before perihelion, they had files and claims. After perihelion, they had validation. The object is real. Its behaviour is anomalous. The sensors captured everything. The story is no longer theoretical. There's another possibility worth considering. Maybe this wasn't a lone whistleblower. Maybe it was internal factional pressure. Intelligence agencies and military organisations aren't monolithic. They contain competing groups with different priorities, different views on secrecy and disclosure. One faction might believe the information should remain classified indefinitely. Another faction might believe the public has a right to know, that transparency serves a greater good. Leaks are often the result of these internal tensions spilling into the open. The question we're left with is uncomfortable. If someone prepared for 3i Atlas 20 years in advance, what did they know? How did they know it? And what else might be coming that we haven't been told about? The timeline suggests more than just good planning or lucky predictions. It suggests foreknowledge of something that shouldn't have been knowable through standard astronomical observation. That's the mystery. That's the hook. And it's about to get stranger, because if this infrastructure was built to prepare for something predicted, we need to look deeper at the patterns emerging from the data. We need to examine whether 3i Atlas is truly the first of its kind, or simply the first one we recognised. Part 6. The 3i Atlas Precursor Theory. Here's a question that keeps astronomers up at night. What if 3i Atlas isn't unique? What if it's not even the first? What if we've been seeing objects like this for years and simply didn't recognise them for what they were? The precursor theory suggests that 3i Atlas might be the most obvious example of a phenomenon that's been occurring in our solar system for longer than we've acknowledged. It's the one we finally caught with the right instruments at the right time, but it might not be the first visitor. Unexplained transients appear in astronomical data more often than most people realise. A transient is any brief, temporary event, a flash of light or an unusual signal that appears and disappears quickly. Most transients have boring explanations: instrument glitches, cosmic rays hitting detectors, satellites passing through the field of view, but some transients resist explanation. They show up in multiple independent observations, ruling out single instrument failures. They exhibit spectral signatures that don't match known phenomena. They happen when and where nothing should be happening. In 2009, the Atlas Survey System, the same network that later identified 3i Atlas, recorded a brief brightening event in a region of sky with no catalogued objects. The transient lasted approximately 6 hours, showed a green-biased spectrum consistent with cyanogen emission, and then disappeared. It wasn't tracked. At the time, nobody knew what to make of it. Cyanogen appears in comets, but this wasn't near any known comet. It could have been a fragment that broke off something larger, or a small object that happened to pass through the detector's field of view at just the right moment. The event was logged and forgotten. 2013 brought another anomaly. A different survey telescope captured what observers initially thought was a satellite glint, a reflection of sunlight off a tumbling piece of space debris. Except the spectrum was wrong. The light contained ionized nickel lines, bright emissions at specific wavelengths that don't appear in satellite reflections. Nickel emissions come from high-energy processes, from solar flares, or supernova remnants or extremely hot plasma. They shouldn't appear in what looks like a tumbling rock in near-Earth space. The observation lasted about 4 hours before the object moved out of the telescope's field of view. No follow-up observations were possible because nobody knew where to point their telescopes. 2018 gave us the strangest pre-Atlas event. Multiple observatories across 3 continents detected what was first classified as a fast-moving asteroid, then reclassified as a probable comet based on a faint coma, then reclassified again as unknown. The object exhibited unusual polarization patterns, meaning the light reflecting off it had been organized in ways that don't happen with normal space rocks or comet nuclei. Polarization tells you about surface structure, about the geometry of particles scattering light. This object's polarization signature changed over the course of 8 hours, cycling through orientations that suggested either extremely rapid rotation or surface activity that modified the shape of its particle cloud in real time. Each of these events shares characteristics with 3i Atlas. The cyanogen spikes, the ionized nickel lines, the unusual polarization patterns, they're all present in the spectrum of 3i Atlas during its brightening phases. But in 2009, 2013, and 2018, we didn't have the context to recognise these signatures as potentially related. They were curiosities, filed away in databases, occasionally discussed in papers about unusual transients, but never connected into a coherent pattern. Until now. If you assume 3i Atlas represents a category of object rather than a unique occurrence, suddenly those earlier events take on new significance. They might have been failed detections, objects that pass through our observational window too quickly for detailed study. They might have been smaller versions of the same phenomenon, less dramatic. less obvious. Or they might have been earlier arrivals in a sequence that's been ongoing for longer than we've had instruments capable of detecting it. The timing of these transients correlates, loosely but noticeably, with something else. Classified sensor blackout periods. Certain military surveillance satellites and ground-based radars experience scheduled maintenance windows when they go offline for calibration, software updates, or hardware replacement. These blackouts are necessary and normal, but the dates sometimes align with unexplained astronomical transients. 2009's cyanogen event occurred during a 12-hour blackout of Northern Hemisphere space surveillance radars. 2013's nickel emission transient happened 3 days after a documented gap in satellite tracking data. The 2018 polarization anomaly appeared during what official records describe as sensor recalibration across multiple tracking stations. Coincidence is always the easiest explanation. Military systems need maintenance. Maintenance schedules are planned months in advance. There's no reason to suspect a connection between routine sensor blackouts and astronomical curiosities. Except the pattern exists. If you're looking for it, if you assume someone might have been tracking these events with classified assets and choosing to take surveillance systems offline during certain windows to avoid creating public records of their observations, suddenly the coincidences accumulate into something more structured. The benign hypothesis remains straightforward. Those earlier transients were unrelated astronomical phenomena, interesting but not connected to 3I Atlas. The spectral similarities are coincidental. Cyanogen appears in lots of comets. Ionized nickel can be produced by solar radiation hitting certain materials. Unusual polarization happens when you observe small particles at odd angles. There's no need to invoke precursor events or patterns. The speculative counterpart is harder to dismiss if the 3I Atlas leaks are authentic. If a surveillance infrastructure was built over 20 years to detect and track objects like 3I Atlas, if that infrastructure was operational and watching, then it would have detected any similar objects that passed through the inner solar system during that time. The absence of public announcements about such detections doesn't mean they didn't occur, it means they weren't disclosed. Precursor events matter for a specific reason. They could validate the Cassandra paper's 20-year timeline. If 3I Atlas is the fourth or fifth object of its type rather than the first, if earlier arrivals were incomplete or failed to exhibit the full range of anomalous behaviours, then the timeline makes more sense. You don't build a comprehensive surveillance network based on a single prediction. You build it based on a pattern. You build it because you've seen this before, because you know it's going to happen again, because next time you want to be ready with every sensor, every wavelength, every capability you can bring to bear. The existence of precursors would also imply regularity. Objects don't arrive randomly from interstellar space at convenient intervals. The galaxy is big. The spaces between stars are incomprehensibly empty. For multiple objects exhibiting similar characteristics to enter our solar system within a decade or two suggests either extraordinary coincidence or something else, a trajectory, a pattern, a reason. Which brings us to the most troubling aspect of 3I Atlas's behaviour. It's not moving the way gravity alone would move it. Part 7. Non-gravitational acceleration signatures. Gravity is reliable. It's one of the few things in the universe you can absolutely count on. Two objects with mass attract each other according to a simple equation. The force depends on how massive they are and how far apart. If you know those numbers, you can predict exactly how an asteroid, comet or spacecraft will move through space. This is how we navigate probes to Mars, how we calculated the trajectory of Voyager leaving the solar system, how we know where Halley's Comet will appear decades in advance. Gravity doesn't surprise us, except sometimes it does. Or rather, sometimes objects don't move exactly the way gravity alone would move them. Comets are the usual suspects. When a comet gets close to the Sun, ice on its surface vaporizes, creating jets of gas that act like tiny rocket engines. These jets push the comet slightly off its predicted path. The effect is called non-gravitational acceleration, and it's well understood. You measure the comet's position over time, compare it to where gravity alone says it should be, calculate the difference, and attribute the discrepancy to outgassing forces. 3I. Atlas exhibits non-gravitational acceleration. That part isn't unusual. What's unusual is the magnitude and direction of the force. Standard comet outgassing creates acceleration vectors that point roughly away from the Sun, because that's where the heat comes from. The sun heats the side facing it. Ice vaporizes on that side. Gas jets away from the sun, pushing the comet in the opposite direction. It's not perfectly uniform because comets tumble and rotate, but the average effect is predictable. 3i Atlas's measured deviation is 15.4 arc-minutes over its observed trajectory. That's an angular measurement, the way astronomers quantify positions on the sky. To put it in perspective, the Moon appears about 30 arc-minutes wide from Earth. So 3i Atlas deviated from its predicted path by roughly half the apparent width of the Moon. That translates to a lateral displacement of approximately 1.1 million kilometres by the time it reached perihelion. That's not a tiny nudge. That's a significant sustained force acting over months. The direction of the force doesn't match standard outgassing models. If you calculate where the push should be coming from based on the object's orientation to the Sun and its rotation, you get predictions that don't match observation. The measured acceleration vector points at an angle that doesn't align with the nucleus to Sun direction. It's as if something is pushing 3i Atlas from the side rather than from the Sun-facing hemisphere. Several natural explanations exist, and scientists are working through them. Maybe the nucleus has an unusual shape that channels out gassing in non-standard directions. Maybe subsurface cavities create jets that emerge from unexpected angles. Maybe the rotation axis is tilted in a way that creates asymmetric heating patterns. All of these are plausible for ordinary comets, but the magnitude of the effect, that million-kilometre deviation, suggests forces stronger than typical comet outgassing produces. This is where speculation begins to sound like science fiction, but it's speculation grounded in real physics. Plasma sails are a theoretical propulsion concept. You generate a magnetic field around your spacecraft, and that field interacts with the charged particles streaming from the sun, the solar wind. The interaction creates force, pushing your spacecraft like wind filling a sail. It's not science fiction. We've studied the physics. We've built small-scale demonstrators. The technology could work. A plasma sail doesn't require engines or fuel. It requires a way to generate and shape magnetic fields, and a plasma envelope to interact with those fields. 3i Atlas has a plasma envelope. The leaked images show it clearly, a structured cloud of ionized gas surrounding the nucleus. The cardinal plasma jets, those four streams extending in geometric patterns, could theoretically be shaped by magnetic fields if you assume the object can generate such fields somehow. The acceleration pattern would fit plasma sail dynamics. You're not getting thrust from rocket engines pointing in specific directions. You're getting force from interactions between your magnetic field and the ambient solar wind, and that force can point in directions that don't align with the sun depending on how you shape your fields. You could, theoretically, produce lateral acceleration, sideways thrust that pushes you off a standard gravitational trajectory. Let me emphasize that this is speculative. There's no direct evidence 3i Atlas is using plasma sail propulsion, or any kind of propulsion. We're observing anomalous acceleration and trying to explain it. Plasma sails represent one possible explanation that happens to fit the observed data better than conventional outgassing. But better fit doesn't mean correct. It means worth investigating. Oumuamua, the first confirmed interstellar object that passed through our solar system in 2017, exhibited similar acceleration anomalies. That case generated intense scientific debate. Some researchers argued for exotic comet behaviour, maybe with pure hydrogen ice that wouldn't leave visible trails. Others suggested more speculative explanations. The debate never fully resolved because Oumuamua left the solar system before we could study it thoroughly. It was discovered after its closest approach to the Sun, giving us only limited observational windows. 3i Atlas is different. It was allegedly monitored from much farther out, possibly from beyond the heliopause, by systems we're only now learning existed. If the leaks are accurate, we have months or years of continuous tracking data, not just a few weeks of observations. That data could show whether the acceleration is constant or variable, whether it correlates with the object's rotation or orientation, whether it's truly anomalous or just poorly understood comet physics. The Cassandra paper predicted objects that would interact with solar fields in unnatural ways. That's the language it used. Unnatural. Not artificial, not designed, but unnatural, meaning not following standard physical processes we've observed before. The paper discussed how such objects might require tracking systems capable of measuring tiny accelerations, how you'd need continuous observation to distinguish between gravitational motion and other forces, how standard celestial mechanics software would need modification to handle objects exhibiting these characteristics. 20 years before 3i Atlas appeared, someone was writing about exactly the kind of behaviour it exhibits. The question is whether they were predicting or describing. Were they theorising about possibilities, or were they explaining something they already knew? The plasma envelope around 3i Atlas might hold answers. It's not just a cloud of gas, it's organised in ways that don't match normal cometary behaviour. Part 8. The Plasma. Envelope Mystery. Comets are messy. They're dirty snowballs, mixtures of ice and rock and organic compounds that get heated by the sun and spew material in all directions. The plasma envelope, the cloud of ionised gas surrounding the nucleus, should be chaotic. It's formed by solar radiation breaking apart molecules, by solar wind blowing charged particles outward, by the comet's rotation creating turbulence. You expect asymmetry, you expect variation, you expect disorder. That's what every comet we've studied looks like. Every comet except 3i Atlas. Polarimetric data from 2025 observations shows something unusual. Polarimetry measures how light waves are oriented, how they oscillate as they travel through space. When light interacts with particles, it becomes polarized in patterns that reveal information about those particles' size, shape, and distribution. Professional astronomers use polarimetry to study dust clouds, planetary atmospheres, any situation where you're trying to understand the structure of something too far away to see directly. 3i Atlas's plasma envelope exhibits layered structure. Multiple distinct shells of emission at different radii from the nucleus, each with its own characteristic polarization signature. The inner shell shows polarization consistent with small particles, sub-micron grains typical of comet dust. The middle shell has larger polarization values suggesting different particle sizes or densities. The outer shell exhibits polarization patterns that don't match any standard comet model. It looks almost like the plasma is organized into discrete zones rather than blending smoothly outward the way normal cometary coma do. Stable shells shouldn't exist. Solar wind varies constantly, pushing on the plasma with changing pressure. The comet rotates, creating centrifugal forces that should distort any structure. Outgassing happens in bursts, injecting new material irregularly. All of these effects should smear any initial structure into a chaotic mess within hours, but the shells persist. They're visible in observations taken days apart, maintaining their relative positions, suggesting something is actively organising the plasma, rather than just letting natural forces dominate. The Cassandra paper included a section on interstellar field interacting bodies that reads like a prediction of exactly this. The authors discussed how objects spending millions of years in deep space might accumulate unusual charge distributions, how interaction with interstellar magnetic fields could create organised plasma structures, how these structures might persist even when the object entered a solar system. They even presented theoretical curves showing how emission intensity should vary with radius if plasma were being actively shaped by magnetic fields rather than just flowing freely. Those curves match 3i Atlas's observed emission profile with uncomfortable accuracy. The paper's Figure 7, a theoretical plot of emission intensity versus distance from nucleus for a field-structured plasma envelope, looks almost identical to actual measurements from 3i Atlas taken 20 years later. Either the authors were incredibly lucky in their theoretical modelling, or they had access to observational data that shouldn't have existed in 2005. Three interpretations compete. The first is purely natural. Maybe 3i Atlas exhibits rare but entirely physical behaviour. Maybe interstellar objects really do behave differently from solar system comets, because they're travelling faster, because they've been subjected to different radiation environments, because their internal structure formed under different conditions. The shells could be real physical phenomena we've never observed before simply because we've only studied two other interstellar objects, and neither exhibited this behaviour. But that doesn't make it impossible, just unusual. The second interpretation involves semi-natural processes shaped by unusual conditions. Maybe 3i Atlas passed through regions of the heliopause where magnetic field topology is complex. Maybe it picked up organised charge distributions during its journey through interstellar space. Maybe interaction between its nucleus's magnetic properties, if it has any, and the solar wind creates standing wave patterns in the plasma that look artificial but arise from known physics operating in unfamiliar regimes. The third interpretation is the one that generates controversy: engineered plasma shaping. If you wanted to protect a spacecraft travelling through interstellar space, you'd surround it with plasma. Charged particles deflect cosmic rays, absorb micrometeor impacts, provide shielding against radiation. You'd want that plasma organised, not chaotic, so you'd use magnetic fields to maintain structure. The shells would be different zones serving different functions. Inner shell for physical shielding, middle shell for radiation absorption, outer shell for interaction with the external environment. None of this proves anything artificial. Proving artificiality requires finding unambiguous signs of design, patterns that absolutely cannot occur naturally. Organised plasma alone doesn't reach that threshold, but combined with everything else, the non-gravitational acceleration, the geometric emission patterns, the 20-year surveillance infrastructure, the list of anomalies accumulates. At some point, calling everything a coincidence becomes harder than considering alternatives. There's another anomaly that's been bothering planetary scientists. 3I Atlas's brightness doesn't correlate with water loss the way it should. When comets get close to the Sun, they brighten because ice vaporizes, creating more surface area of reflected particles. The amount of brightening should roughly track the amount of water vapor being produced. JWST, the James Webb Space Telescope, took spectroscopic measurements of 3I Atlas during its approach. The data showed less water vapor than the brightness would predict. It's brighter than it should be for the amount of ice it's losing. This could mean the nucleus is made of material more reflective than typical comet ice. It could mean the particle size distribution in the coma is unusual, creating more efficient light scattering. Or it could mean the brightness isn't coming primarily from reflected sunlight and particle scattering. If significant emission is coming from the plasma itself, from ions recombining and releasing photons, from electrical processes in the magnetized envelope, then the brightness-water correlation breaks down. You'd see light that doesn't correlate with ice sublimation because it's being produced by different physics. The classified sensor data, if it exists as the leaks suggest, would resolve these questions definitively. Multispectrum analysis across dozens of wavelengths, continuous monitoring showing how the plasma envelope evolves over time, high-resolution imagery revealing fine structure in the shells, all of this would either confirm natural processes or reveal patterns inconsistent with any known physics. That data hasn't been released. Maybe it will never be released. Maybe it's locked in classified databases, analysed by scientists bound by secrecy agreements, informing policy decisions the public isn't part of. Which brings us to the most intriguing hypothesis to emerge from analysis of the Oracle 6 leaks. Someone might have tried to get a closer look. Not just observe from 60,000 kilometres at L1, actually intercept the object during its approach. Part 9. The Lagrange Point Intercept Hypothesis. One of the leaked diagrams deserves closer examination. It's labelled Configuration 12, dated 9 months before 3I Atlas's official discovery, and it shows Oracle as in an unusual orientation. The spacecraft's sensor array, normally aligned for continuous wide-field surveillance, is reoriented to focus on a single point in space. The diagram includes trajectory lines showing an object approaching from the galactic plane, passing through Oracle 6 field of view at a precise angle. Annotation boxes reference optimal backlit geometry, minimal solar interference, and intercept window duration 7 hours. An intercept in this context doesn't mean a physical rendezvous. It means positioning your sensors to capture an object at the ideal moment when lighting conditions, distance, and viewing angle combine to give maximum data quality. Ground-based astronomers do this all the time, planning observations months in advance to catch asteroids during close approaches when they're brightest and easiest to study. But this diagram suggests something more complex. It suggests Oracle 6 was repositioned specifically to capture 3I Atlas during a narrow observational window using the Sun as a backlight to reveal details that wouldn't be visible from other angles. Why that specific configuration matters is subtle, but important. When you observe an object with the Sun behind it from your perspective, you're seeing its shadow, its silhouette, and any material it's surrounded by becomes dramatically more visible. Diffuse plasma that would be nearly transparent under direct lighting suddenly shows structure when backlit. You can map variations in density, identify gaps or voids, see geometric patterns that would otherwise remain hidden. It's the difference between trying to see smoke in daylight versus seeing smoke against a bright background. The contrast reveals everything. Rumours exist, unverified and unverifiable, that Oracle 6 captured an unusual electromagnetic event during this intercept, not visible light. Something in the radio spectrum, a brief burst of organised signal activity that coincided with one of 3i Atlas's brightness jumps. The rumours describe the signal as structured but non-linguistic, meaning it had patterns, repetition, characteristics that distinguished it from random noise, but didn't resemble any known communication protocol. These rumours circulate in the same aerospace forums where people first mentioned the non-SOHO L1 resident craft years ago. There's no proof, just people who claim to know people who saw something strange. Let's be clear about what's verified. There are no public records of Oracle 6 conducting an intercept mission. There's no NASA announcement, no press release, no scientific paper describing such observations. What we have is a leaked diagram showing a configuration optimized for exactly that kind of mission, dated to suggest it occurred before public discovery of 3i Atlas. Either the diagram is fabricated, part of an elaborate hoax, or it documents a classified operation. An L1 intercept makes technical sense. The geometry provides advantages you can't get from ground-based observation. You're above Earth's atmosphere, eliminating all the distortion that plagues telescope imagery. You're at a fixed point relative to the Sun-Earth system, making trajectory planning straightforward. You're positioned to observe objects approaching from the direction of the Sun, which is exactly where 3i Atlas came from during its inbound trajectory. If you wanted to study an interstellar object in detail before it became visible to ground telescopes, L1 is where you'd put your sensor. The absence of any public mission to approach 3i Atlas is telling. When Oumuamua was discovered in 2017, there was immediate discussion of sending a probe to catch it, to study it up close before it left the solar system. Multiple mission concepts were proposed, feasibility studies were conducted, and ultimately nothing happened because the object was moving too fast, and we found out about it too late. The window closed before any mission could be organised. 4. 3i Atlas, there's been silence on that front. No announced missions, no public discussion of close approach studies, no space agencies proposing to send spacecraft for intercept. Either everyone learned from Oumuamua that such missions aren't practical, or there's no need for public missions because classified assets are already conducting those observations. Scientists did detect unusual electromagnetic emissions before 3i Atlas's discovery. Not radio signals, but brief increases in background magnetic field strength recorded by solar observatories. These events are typically attributed to solar activity, coronal mass ejections, or instrument noise. But several occurred at times when solar activity was quiet, when no obvious source existed. The events were brief, lasting minutes to hours, and showed polarization characteristics that didn't match standard solar emissions. Data gaps exist around those same periods, not blackouts exactly, but windows when certain instruments were in maintenance mode, or when data wasn't archived normally. These gaps are small, often just hours, but they cluster around the times when unusual electromagnetic events were detected. Maybe that's coincidence. Maybe routine maintenance happened to occur during the same windows when instruments detected anomalies. Or maybe data was collected but not publicly released. The theory that no one wants to voice openly, the hypothesis that sits at the edge of scientific respectability, connects all of these pieces. 3i Atlas exhibits organised plasma structures, geometric emission patterns, non-gravitational acceleration, and electromagnetic signatures that don't match natural phenomena we've observed before. A surveillance infrastructure built over 20 years tracked it during approach. The scientific establishment is cautious about speculating why, but the pattern suggests something beyond ordinary comet behaviour, which leads to the most controversial theory emerging from analysis of these anomalies. Part 10. The theory no one wants to touch. It's a beacon, not a visitor. Let me introduce you to a concept that makes scientists uncomfortable, not because it's ridiculous, but because it's unfalsifiable. The idea of interstellar markers, objects that travel between stars not to explore, but to indicate, to mark coordinates, to serve as reference points for something or someone with the capacity to track such markers across galactic distances. It's speculative. It touches on ideas adjacent to SETI, the search for extraterrestrial intelligence, but approaches the question from a different angle. Not communication, not probes gathering data, but beacons broadcasting or marking locations. Beacon behaviour differs fundamentally from probe behaviour. A probe explores. It carries sensors, It collects information about its environment. It reports back to whoever sent it. A probe needs agency, decision-making capability, the ability to adapt to what it finds. A beacon just marks. It emits signals, it occupies a position, it provides a reference point. Beacons are simpler. They don't need intelligence or autonomy. They just need to be detectable. 3i Atlas's geometric emissions resemble timed pulses if you look at them in the right framework. The brightness fluctuations aren't random. They occur at intervals that show weak periodicity, not strictly regular but displaying patterns. The plasma jets maintain their cardinal orientations despite the object's rotation, as if they're being actively stabilized rather than just flowing naturally. If you were designing a marker that needed to be visible across astronomical distances, you'd want it to be distinctive, to stand out against the background noise of natural phenomena. Geometric patterns achieve that. Random processes rarely produce symmetry. Organization implies signal. The Cassandra paper's final section discussed non-biological informational carriers in language carefully chosen to avoid explicit SETI implications. The authors talked about objects that could convey information through their physical state, through patterns in their emissions, without requiring active computation or intelligence. A crystal encodes information in its structure. A pulsar broadcasts regularity through its rotation. An artificial object could encode information through designed features that emerge when specific conditions occur, like solar heating triggering emissions in planned patterns. Natural alternatives must be emphasized. Pulsars are natural and produce incredibly regular timing. Masers, natural microwave amplifiers in space, create coherent beams that look artificial until you understand the physics. Interstellar clouds organize into filaments and shells through gravity and magnetic fields, producing structure without intent. Nature creates patterns all the time. Finding patterns doesn't prove design. But 3i Atlas combines several patterns simultaneously. Geometric plasma jets, non-gravitational acceleration in non-standard directions, organized shell structure in the plasma envelope, electromagnetic emissions coinciding with brightness events. Each individual anomaly has possible natural explanations. The combination is harder to explain naturally. It's like finding a rock that's pyramid-shaped, perfectly smooth, covered in symbols, and emitting radio waves. Any one feature could be natural. All of them together make you wonder. If 3i Atlas is a beacon, what's it marking? The simplest answer is location. The solar system's coordinates in the galaxy. The sun's position relative to interstellar reference frames. Objects that emit at multiple wavelengths, that maintain geometric patterns, that follow predictable trajectories could serve as navigational markers for anyone capable of tracking them. You scatter them through a region of space, each one distinct, and you have a coordinate grid, a more speculative answer involves timing. Maybe the beacon isn't marking where but when. If 3i Atlas is part of a sequence, if similar objects arrive at regular intervals, the pattern itself contains information. The intervals between arrivals, the slight variations in their trajectories, the differences in their emission spectra, all of this could encode data for anyone able to observe multiple instances and compare them. The most speculative answer is that it's marking an event, not exploring, not navigating, but indicating something about to happen, or something that already happened elsewhere. This interpretation ventures into territory that scientists avoid because it's not testable. You can't design experiments around cosmic prophecy. But if you accept that 3i Atlas exhibits anomalous behavior, if you accept that similar objects might have preceded it, if you accept that a surveillance infrastructure existed to watch for it, then the beacon hypothesis provides a framework that fits the data. The Cassandra paper's title becomes more meaningful in this context. Cassandra, from Greek mythology, cursed to speak true prophecies that nobody believed. The paper warned about interstellar objects arriving with unusual characteristics. It laid out detection architecture to monitor for them. It described behaviors matching what 3i Atlas exhibits. Was it prophecy? Was it preparation? Or was it explanation? A careful academic discussion of something already known through classified channels? None of this proves the beacon hypothesis. Science requires evidence that can distinguish between competing theories, experiments that give different results depending on which theory is correct. We don't have that here. We have patterns that might be meaningful or might be coincidence. We have leaked files that might be authentic or might be fabricated. We have a surveillance infrastructure that might have tracked this object for 20 years, or might have been built for other reasons entirely. What we definitely have is an object that doesn't behave like anything we've seen before. An object that was apparently anticipated by classified programs we're only learning about through leaks. An object arriving at a moment when multiple breakthroughs in physics and astronomy are changing how we understand the universe. That's not coincidence. That's context. And the context is about to get stranger. Part 11. New 2025 Quantum Sensor Breakthrough. Something changed in 2025 that most people didn't notice. While everyone was watching 3i Atlas brighten and fade, while leaked files were circulating through private forums, while conspiracy theories and scientific papers competed for attention, a different story was developing in laboratories and research facilities. A story about sensors capable of detecting things we couldn't detect before. Quantum entanglement, a phenomenon Einstein called spooky, action at a distance, moved from theoretical physics to practical engineering. Entanglement means that two particles can be connected in ways that transcend normal space and time constraints. Measure one particle's state, and you instantly know something about the other particle's state, even if they're separated by enormous distances. This doesn't violate relativity because you can't use entanglement to transmit information faster than light. The correlation is instant, but you can't control what the correlation reveals. It's like having two coins that always land on opposite sides when flipped, but you can't choose which side either coin shows. Einstein hated this. He spent years trying to prove entanglement couldn't be real, that quantum mechanics must be incomplete, that hidden variables would eventually explain away the apparent spookiness. He lost that argument. Experiments over decades confirm that entanglement is real, that particles genuinely share states across arbitrary distances instantaneously. It's one of the most thoroughly verified predictions of quantum mechanics, tested in laboratories worldwide, demonstrated countless times. We've moved past asking if it's real to asking what we can do with it. For deep space sensing, entanglement offers a revolutionary capability. You can create sensor networks where measurements at one location correlate with conditions at another location, allowing you to build interference patterns that reveal information about objects between the sensors. It's similar to how radio telescope arrays combine signals from multiple dishes to create resolution equivalent to a telescope the size of the distance between dishes. Quantum sensors take this concept further, using entanglement to create baselines that span solar system distances. The technical challenge is maintaining entanglement. Quantum states are fragile, interact with the environment, and the entanglement breaks, a process called decoherence. Photons travelling through space encounter stray particles, temperature variations, electromagnetic fields, any of which can destroy the quantum correlation you're trying to maintain. Early experiments could maintain entanglement for microseconds over meters. Gradually, researchers extended that to milliseconds over kilometers. But space-scale distances, thousands or millions of kilometers, seemed impossible with near-term technology. The breakthrough announced in 2025 involved stable entanglement over unprecedented distances. Previous experiments maintained entanglement for kilometers, or at most a few thousand kilometers. The new systems demonstrate entanglement stability over distances comparable to the Earth-Moon separation. That's the same scale as L1, where Oracle 6 allegedly operates. It's the same scale you'd need to create a solar system-wide detection grid. The key innovation involves what researchers call environmental decoupling nodes. These are intermediate stations that don't measure the entangled particles directly, but refresh them, swapping quantum states in ways that preserve entanglement while filtering out environmental noise. Think of it like relay stations in a communications network, except instead of amplifying signals, they're preserving quantum correlations. The mathematics is complex, the engineering harder still, but the principle is straightforward. You can't fight decoherence directly over enormous distances, but you can create checkpoints where quantum information is transferred to fresh particles that continue the journey. NASA announced the breakthrough in a low-key press release that got buried beneath more dramatic space news. The language was careful, emphasizing research applications and far future potential, but people who understand what quantum sensors enable recognize the implications immediately. You're not just building better telescopes, you're creating measurement capabilities that fundamentally change what's detectable from how far away. DARPA, the Defense Advanced Research Projects Agency, and NASA jointly proposed implementing quantum baselines for near-Earth object detection. The public documentation describes using entangled photon pairs to improve sensitivity for detecting faint asteroids. The unclassified proposals discuss detection thresholds, signal-to-noise improvements, and theoretical capabilities that sound modest. Improvements measured in percentages, slightly better detection ranges, marginally improved positional accuracy. Nothing revolutionary if you read the public version, but the classified annexes known to exist but not publicly available almost certainly discuss applications beyond asteroid tracking. When defense agencies and space agencies collaborate on quantum technology proposals, the unclassified portions are deliberately sanitized. They describe the minimum capabilities necessary to justify the program to public oversight. The classified sections describe what you really intend to build, what the technology actually enables when pushed to its limits. Quantum sensors operating at solar system scales could detect disturbances in space-time itself. Not just electromagnetic radiation, not just particle flows, but the subtle warping of space caused by mass and energy moving through it. This isn't gravitational wave detection in the traditional sense. Those require objects like colliding black holes creating catastrophic space-time ripples. This is something subtler, using quantum correlations to measure how background quantum fields vary across distances, changes so small they're normally lost in noise but which quantum entanglement makes visible. An object entering the solar system disturbs everything around it. Its gravity, however weak, pulls on nearby matter. Its magnetic field, if it has one, interacts with the interplanetary medium. Its plasma envelope, if present, creates compression waves in the solar wind. Each effect is tiny, barely measurable by conventional instruments. But if you have entangled sensors distributed across the solar system, you can correlate these tiny signals, building up a complete picture of the disturbance from data that would be meaningless in isolation. Quantum sensors could confirm Cassandra-style detection grids retroactively. Here's what that means. If you've been observing the sky with conventional sensors for 20 years, you have archives full of data showing objects at various distances, various brightnesses, various trajectories. Most of those objects are well understood, some are anomalous. With quantum sensors, you could reprocess the archives, looking for faint signatures that conventional sensors missed, correlating observations across different platforms in ways that reveal patterns invisible to normal analysis. The archives aren't just images and spectra, they include environmental measurements, magnetic field readings from spacecraft throughout the solar system, particle detector data from radiation monitors, gravitational micro-lensing events, where distant objects briefly brightened as something passed in front of them. Each individual measurement seemed random or uninteresting when collected, but with quantum correlation analysis, you could connect measurements separated by millions of kilometers and months of time, revealing that they were all responses to the same object, something passing through that disturbed multiple sensors in coordinated ways. Specifically, quantum sensors might reveal signatures of objects passing through the heliopause, the boundary of our solar system, years before they become detectable through normal means. The heliopause is turbulent, full of charged particles and magnetic field interactions. An object entering that region disturbs the environment in subtle ways. With sensitive enough instruments, you might detect those disturbances long before you can see the object itself. It's like seeing ripples on a pond before you see the stone that caused them. The heliopause is approximately 18 billion kilometers from the Sun, roughly 120 astronomical units. Light takes 16 hours to travel that distance. An object moving at typical interstellar velocities, say 20 kilometers per second, needs several years to traverse from the heliopause to the inner solar system where Earth orbits. If you can detect it at heliopause crossing, you have years of advance warning, years to prepare observation campaigns, years to position assets, calibrate instruments, develop analysis software, years to decide how to respond if the object exhibits anomalous characteristics. If Oracle 6 or similar platforms incorporated early-stage quantum sensor technology, even less capable than what's being announced now, they could have detected 3i Atlas as it crossed the heliopause. That would provide years of advance warning, enough time to plan intercept missions, calibrate sensors, prepare analysis protocols. It would explain how someone knew to position assets for observation before official discovery. Defense and intelligence communities have a long history of deploying technology before it becomes public knowledge. Stealth aircraft flew for years before their existence was acknowledged. Satellite reconnaissance capabilities remained classified decades after their development. Quantum sensor technology, if it works as described, provides such overwhelming advantages for space surveillance that it would inevitably be classified. You'd develop it, test it, deploy it secretly, and only acknowledge its existence years later, when the technology matures enough that potential adversaries will develop it independently anyway. The timeline works. If quantum sensor development began in the early 2000s, around the time the Cassandra paper appeared, and if prototype systems were operational by the 2010s, they could have been monitoring the heliopause for years before 3i Atlas arrived. The public announcement in 2025 would then represent not a breakthrough, but a declassification, a decision to reveal capabilities that already exist because hiding them no longer serves strategic interests. The implications extend beyond 3i Atlas. If quantum sensors can detect heliopause breaches, they can potentially distinguish between natural objects and anomalous ones based on how they disturb the boundary region. Natural comets and asteroids create predictable patterns. Their gravitational effects, their magnetic properties, their interaction with solar wind plasma all follow physics we understand. Anomalous objects, things exhibiting organized plasma envelopes or non-gravitational acceleration, would create different disturbance patterns. The disturbance signature would depend on the object's composition, structure, and activity level. A simple ice ball creates one pattern. A metallic asteroid creates another. An object surrounded by organized plasma creates a third, distinctive pattern that stands out immediately. You wouldn't need to wait for the object to reach the inner solar system to know it's unusual. You'd see the anomaly in how it crosses the heliopause, in how the boundary responds to its passage. You could, theoretically, pre-screen objects as they enter the solar system. Flag the interesting ones for detailed observation. Ignore the boring rocks and ice balls that pose no threat and exhibit no unusual properties. Build a prioritized watch list of objects worth tracking with your most capable sensors. This is speculation, but it's speculation grounded in what quantum sensor technology makes possible. The efficiency implications are enormous. Currently, we discover objects through surveys that scan the sky repeatedly, looking for things that move between observations. It's resource intensive, requires powerful telescopes, and mostly finds ordinary asteroids. If you could pre-screen at the heliopause, you'd focus resources only on objects worth studying. Everything else, the vast majority of interstellar debris, you'd catalogue briefly and ignore. Your limited observation time and processing capability would go toward genuinely interesting targets. For a classified surveillance program, this capability would be invaluable. You're not trying to publish papers or share data with the scientific community. You're trying to identify potential threats or opportunities before anyone else knows they exist. Quantum sensors give you years of advance warning. You can study an approaching object in detail, determine its nature, decide how to respond, and only reveal its existence publicly if that serves your interests. Gravitational wave astronomy has revealed another layer of structure to the universe that quantum sensors might help exploit. The gravitational wave background, a constant hum of space-time distortions from sources throughout the universe, shows patterns that we're only beginning to map, and those patterns might connect to what we're observing with 3i Atlas in ways that suggest the galaxy is far more structured and active than we've imagined. Part 12, December 2025. Breakthrough in gravitational wave background mapping. The universe hums. Space-time itself vibrates with gravitational waves, ripples created by massive objects accelerating somewhere in the cosmos. Black holes orbiting each other, neutron stars colliding, galaxies reshaping themselves through gravitational interactions. All of these events send waves through space-time that propagate at light speed. We've been detecting individual gravitational wave events since 2015, spectacular collisions billions of light-years away that create signals strong enough to register in our detectors. But beneath those dramatic events lies something subtler, the gravitational wave background. December 2025 brought the most detailed maps yet of this background signal. Multiple gravitational wave observatories, working together with unprecedented coordination, produced directional maps showing where in the sky the strongest background signals originate. Previous measurements could detect the background as a general hum. The new data resolves that hum into discrete sources, or at least into regions where the signal is stronger, suggesting concentrated activity. The surprise wasn't that the background exists. Theory predicted it. The surprise was the clustering. Gravitational wave background signals don't distribute evenly across the sky. They concentrate in specific directions, forming patterns that suggest large-scale structure in the distribution of sources. Some regions of the galaxy produce stronger signals than others. Some directions show periodicity, regular variations in signal strength that imply something oscillating or orbiting at cosmic distances. 3 theories compete to explain these patterns. The first invokes dense stellar remnant clusters, regions where old stars have ended their lives and left behind neutron stars or small black holes. These remnants can form binary systems, orbiting each other, creating gravitational waves. If enough of these systems cluster in particular galactic regions, they'd produce the enhanced background signals we're measuring. The second theory discusses large-scale structure filaments, the scaffolding of matter that organizes galaxies into walls and voids spanning hundreds of millions of light-years. These filaments might channel matter in ways that create gravitational wave sources preferentially along certain directions. You'd see concentration of signal along the filaments, reduced signal in the voids between. The third category of theories, less discussed in public but present in technical papers, considers unknown repeating sources. Objects or phenomena we haven't identified yet, producing gravitational waves at regular intervals, possibly detectable individually if we knew where to look but blending into the background when we observe the whole sky at once. Some of the detected trajectories line up roughly with known interstellar object paths. Not perfectly, not in ways that prove connection, but enough to be intriguing. Oumuamua's trajectory, traced backward, points toward a region showing elevated gravitational wave background. 3I Atlas's inbound path, extrapolated back through time, passes through another concentration zone. These could be coincidences. Space is three-dimensional, and any 2 lines will point towards some region if you follow them far enough. But the correlation exists. Here's why it might matter. If interstellar objects aren't random but are following specific trajectories through the galaxy, those trajectories might correlate with the galactic structure revealed by gravitational wave mapping. Objects could be following paths through regions where gravitational wave activity is enhanced, either because those paths formed naturally along gravitational gradients, or because something is using those paths deliberately. That's where speculation becomes difficult to distinguish from pattern-matching instincts run wild. The human brain excels at finding patterns, sometimes too well, seeing connections that don't exist. Gravitational wave concentrations might align with interstellar object trajectories for boring reasons. Both are influenced by galactic structure. Of course they correlate. It doesn't mean anything special, but combined with everything else we're examining, the possibility emerges that the galaxy is more structured than we assumed. Not just physically, in terms of matter distribution, but informationally. If objects are travelling between stars carrying information, whether as probes or beacons or something else, they'd likely follow routes. You don't send probes randomly in all directions. You send them along paths that connect interesting locations, that pass through regions worth surveying, that form a network. Gravitational wave mapping might be revealing that network. Not directly, but through the traces left by activity along the routes. If something is travelling through certain regions frequently enough, if enough objects have passed through over long enough timescales, they might leave signatures. Not footprints exactly, but correlations in the data that suggest preferential paths exist. The breakthrough in gravitational wave background mapping suggests the galaxy is more dynamic than our models predicted. There's structure at scales we didn't expect, there's activity we didn't account for. And that activity might connect to other anomalies we're observing closer to home, including the behaviour of 3I Atlas and the mysterious plasma envelope surrounding it. Recent research into plasma physics itself has revealed something that might explain part of the mystery. Part 13, the new dark plasma research announcement. Plasma is the 4th state of matter after solid, liquid and gas. Heat something enough, and electrons tear free from atoms, creating a soup of charged particles that behaves in ways fundamentally different from ordinary matter. Plasma responds to electric and magnetic fields. It forms structures, creates waves, generates currents. Most of the visible universe is plasma. Stars are plasma. The space between stars is plasma, albeit extremely diffuse. Planetary magnetospheres are filled with plasma. We understand plasma pretty well, or we thought we did. 2025 research announced in December claims the existence of a previously unknown plasma state in heliospheric data. The researchers call it dark plasma, though that name has caused controversy because it implies connection to dark matter, which this isn't. Dark plasma, in their model, is a weakly interacting charged medium that doesn't couple strongly to electromagnetic fields the way normal plasma does. It's still affected by electric and magnetic forces, but less directly, as if there's an intermediate step between the fields and the particle response. The research is speculative but mathematically consistent. The authors analyse data from spacecraft operating at the heliopause, missions like Voyager that have crossed the boundary between our solar system and interstellar space. They found anomalies in particle counts, moments when charged particle detectors registered less than expected given the electromagnetic field measurements. Normal plasma density should correlate with field strength. In these regions, it didn't. Either the instruments were wrong, or something was there that doesn't interact normally with fields. The team behind this research includes physicists from 3 different institutions, people who've spent careers analysing space plasma data. They're not fringe theorists. They're establishment scientists proposing something that sounds radical because the data forces them to. When Voyager 1 crossed the heliopause in 2012, instruments recorded a sharp change in particle composition, exactly as predicted. Solar wind particles decreased, interstellar particles increased. But embedded in that transition were moments, brief windows lasting hours or days, when particle detectors seemed to disagree with magnetometer readings. The magnetic field strength suggested plasma should be present at certain densities. The particle counters showed less. The discrepancy was small, often within error margins, easy to dismiss as instrument drift or calibration uncertainty. Except it kept happening. Voyager 2 crossed the heliopause in 2018 at a different location, different conditions, and showed similar anomalies. New Horizons, though still far from the heliopause, occasionally reports similar particle field mismatches when passing through certain regions of the outer solar system. Each individual instance could be explained away. Collectively, they suggest something systematic, a real phenomenon that our models don't account for. Dark plasma's properties overlap uncomfortably with the unusual plasma envelope seen around 3I Atlas. The stable shell structure, the resistance to disruption by solar wind, the ability to maintain organization despite turbulent external forces, all of these could be explained if the plasma includes a component that doesn't respond immediately to external fields. It would act as a stabilizer, a medium that holds structure while normal plasma flows around it. Think about what this means practically. Normal plasma in space is constantly buffeted by changing conditions. Solar wind speed varies, magnetic field orientation shifts, cosmic rays pass through, ionizing additional particles. Any structure you create in normal plasma disperses quickly, unless you actively maintain it with external fields. But if you had a plasma component that resists external disruption, that maintains its organization through memory of its previous state, rather than immediate response to current conditions, you could build structures that persist naturally. The dark plasma would form a skeleton, a framework that normal plasma fills in around but doesn't disrupt. The mathematical models supporting dark plasma hypothesis invoke particle populations with unusually high internal energy states. These aren't hot in the conventional sense of moving fast. They're energetically excited in ways that decouple their electromagnetic response from simple field interactions. An analogy might be supercooled water, liquid below freezing temperature that doesn't crystallize until disturbed. It's in a metastable state, behaving contrary to what simple thermodynamics would predict. Dark plasma, in this framework, exists in metastable electromagnetic states, neither fully responsive to fields nor fully independent of them. Creating such states in a laboratory would be extraordinarily difficult. You'd need precise control over particle energies, careful management of field geometries, isolation from external perturbations. But nature creates extreme conditions routinely. The heliopause is a shock front where supersonic solar wind suddenly decelerates, where magnetic fields compress and twist, where particles from 2 different stellar environments collide. Maybe those conditions naturally produce metastable plasma states that we've never observed before, because we've never had instruments at the boundary measuring carefully enough. Natural explanations exist. Maybe heliospheric conditions create particle populations with unusual electromagnetic properties. Maybe solar wind turbulence, the chaotic churning of charged particles streaming from the sun, stratifies particles by mass or charge in ways that produce apparent weak interaction. Maybe our plasma physics models need updating to account for conditions we haven't observed before, the transition regions between stellar and interstellar environments. Scientists have proposed similar anomalies before and been proven wrong. In the early days of space exploration, some researchers thought they'd found evidence of exotic plasma physics in the magnetosphere. Turned out their instruments were measuring Earth's upper atmosphere, not space plasma, and the anomalies disappeared once they understood their data better. Extraordinary claims require extraordinary evidence, and the dark plasma claim is extraordinary. The researchers know this. Their papers are full of caveats, alternative explanations, calls for additional observations. They're not declaring victory. They're saying we found something weird, here's a possible explanation, please help us figure out if we're right. But here's where it connects to 3I Atlas in ways that make people nervous. The plasma envelope around that object exhibits exactly the characteristics dark plasma theory would predict for an engineered structure. Not naturally occurring dark plasma created by boundary conditions, but deliberately generated dark plasma shaped into specific geometries. The distinction matters. Natural dark plasma would be diffuse, transient, hard to maintain. Engineered dark plasma could be concentrated, stable, functional. The speculative explanation that makes some physicists uncomfortable suggests dark plasma isn't naturally occurring in significant quantities. Maybe it's manufactured. Plasma can be engineered, shaped through electromagnetic fields, organized into structures that serve specific purposes. Laboratory fusion reactors do this, using powerful magnetic fields to confine plasma hot enough to fuse atoms. If you could generate dark plasma, plasma that doesn't respond strongly to external perturbations, you could create structures that persist in environments where normal plasma would disperse. Imagine you're designing a spacecraft for interstellar travel. You need shielding against cosmic rays, protection from micrometeor impacts, thermal management for the extreme, temperature variations between direct sunlight and shadow. Solid shielding is heavy, expensive to accelerate to interstellar velocities, but a plasma shield, especially one using dark plasma for structural stability, would be lightweight, self-healing, adaptable to changing conditions. You generate it around your craft using electromagnetic coils, maintain it with relatively low power consumption, and have protection superior to any solid material. The 3I Atlas plasma envelope might be partially composed of dark plasma. The shells, the geometric jets, the stability over time, all consistent with a medium that resists external disruption. The research papers discussing this possibility are careful, hedged with qualifications, emphasizing the speculative nature of the claim. But the math works, the observations fit, and if 3I Atlas is surrounded by engineered plasma, that has implications impossible to ignore. We're talking about the difference between finding a new natural phenomenon and finding evidence of technology. Natural phenomena, however strange, remain within the boundaries of known physics. They surprise us, they challenge our models, but they don't fundamentally alter our understanding of our place in the universe. Technology, especially technology we didn't create, changes everything. It means intelligence, capability, intent. It means someone built something, deployed it, sent it travelling through interstellar space for purposes we can only guess at. This is where scientific caution becomes critical. Speculative research can generate hypotheses that fit data without being correct. Multiple theories can explain the same observations. Choosing between them requires additional evidence, experiments that distinguish predicted outcomes. We don't have those experiments yet. We have correlations, patterns, possibilities. Moving from possibility to conclusion requires rigor we can't yet apply. What we need is direct sampling. Send a probe to rendezvous with an object like 3I Atlas. Fly through its plasma envelope with instruments that can measure particle populations, field geometries, energy states directly. Determine if dark plasma exists, if it's concentrated around the object, if it shows signs of artificial generation. That mission is decades away at minimum. 3I Atlas is already receding, moving too fast for any probe we could launch with current technology to catch. By the time we could mount such a mission, we'd need to wait for the next similar object to arrive, unless the classified surveillance network has capabilities we don't know about. Unless Oracle Sixungs or similar platforms can conduct remote measurements that answer these questions without physical proximity. Maybe that data already exists. locked in classified databases, analysed by physicists with security clearances who can't publish their findings. The leaked files suggest comprehensive sensor coverage. Multispectrum imaging would capture plasma emission lines that reveal particle populations. Magnetic field measurements would show field geometries. You could potentially characterize dark plasma remotely if your instruments were sensitive enough and you had extended observation periods. But the accumulation of anomalies continues. Quantum sensors that might detect objects at heliopause crossing. Gravitational wave mapping revealing galactic structure. Plasma physics research suggesting new states of matter, each development independently interesting. Together they create a context where 3i Atlas stops looking like an isolated anomaly and starts looking like the visible edge of something larger. The timing of the dark plasma announcement, December 2025, the same month gravitational wave mapping breakthroughs emerged, the same period when AI systems began flagging similar objects in archived data, feels less like coincidence and more like coordination. Maybe independent research groups reached critical breakthroughs simultaneously. Maybe the scientific community is experiencing a rare moment of convergent progress across multiple fields. Or maybe information is being released deliberately, carefully timed to build a narrative that prepares the public for revelations yet to come. The most recent development, announced as December 2025 progresses, involves artificial intelligence finding patterns humans missed. And those patterns might finally give us the context to understand what 3i Atlas really represents, whether it's unique or part of a larger phenomenon we're only beginning to recognize. Part 14, AI-driven anomaly. Detection upgrade in 2025. Astronomical data is overwhelming. Telescopes across the electromagnetic spectrum capture petabytes of information every night. Images, spectra, time series measurements, all recorded digitally and stored in archives that researchers can access years or decades later. Human astronomers can't review all this data manually. We've always relied on automated systems to flag interesting events, to identify potential discoveries that warrant closer examination. But traditional automated systems are limited. They find what they're programmed to find. If something unexpected happens, something that doesn't fit predefined criteria, it might go unnoticed. Machine learning, particularly deep neural networks, changes that dynamic. AI systems can learn to recognize patterns from examples without being explicitly programmed. Show them thousands of images of normal galaxies, and they'll learn what normal looks like. Then they can flag galaxies that don't look normal, even if the difference is subtle, even if humans haven't previously recognized that particular kind of anomaly. The same principle applies to asteroid detection, stellar spectra, anything where pattern recognition matters. 2025 saw deployment of significantly upgraded AI systems analysing all-sky survey data at massive scale. These systems process decades of archived observations, applying modern machine learning to data collected before such techniques existed. They're not just finding new objects, they're finding patterns in how known objects behave, correlations across datasets that weren't obvious when the data was collected, anomalies buried in noise that conventional analysis methods missed. One AI model, trained specifically on detecting irregular motion patterns, flagged 12 objects exhibiting characteristics similar to 3i Atlas. Not identical. These objects don't show the same geometric plasma jets or stable shell structure, but they exhibit unexplained non-gravitational acceleration, unusual brightness fluctuations, spectral features that don't match standard comet or asteroid models. The objects span observations from the past 15 years, suggesting they were visible in archived data but never recognized as anomalous until AI reviewed the records with fresh perspective. This doesn't imply artificiality. Flagging something as anomalous just means it's statistically unusual, doesn't fit the bulk population of similar objects. Most astronomical anomalies turn out to have boring explanations once studied in detail. Instrument artifacts, rare but natural phenomena, objects observed under unusual conditions that distort our measurements. The AI isn't claiming these 12 objects are artificial or designed, it's just saying they're weird, worth closer examination. What's significant is the rate. If AI flagging identifies 12 Atlas-like objects in 15 years of archived data, and 3i Atlas appeared in 2025, that suggests roughly one such object per year enters our observational sphere. Some are noticed, most aren't. The discovery rate depends on having the right instruments looking in the right directions at the right times. Before AI, we missed most of them. Now we're catching up, reviewing archives with tools that find what humans overlooked. The implications for the Cassandra surveillance network are direct. If objects like 3i Atlas arrive regularly, roughly once per year, then a system watching continuously would detect them routinely. You'd accumulate a catalogue, build a database of characteristics, identify patterns in their arrival times or trajectories. The 20-year timeline makes more sense if multiple objects were detected and studied. If 3i Atlas is simply the most recent and most thoroughly observed example, AI may rewrite our understanding of what counts as rare. Events we thought occurred once per century might actually occur once per year, and we just lack the tools to notice them consistently. This applies across astronomy. Fast radio bursts, gamma-ray transients, unusual stellar spectra, all previously considered rare, might be common but hard to detect. As our instruments improve and our analysis techniques advance, the universe reveals itself as more active, more variable, more interesting than we previously believed. For 3i Atlas specifically, AI could retrospectively identify precursor events with greater confidence. If the 12 flagged objects include some that passed through similar spatial regions, followed similar trajectories, exhibited similar spectral features, you'd have evidence of a pattern. Not proof of artificial origin, but evidence that these aren't random isolated phenomena. Something systematic is occurring. The question is whether the Cassandra surveillance network used similar AI techniques years before they became available publicly. Military and intelligence organizations often deploy technologies a decade or more ahead of civilian equivalents. The computing power, the algorithms, the training data, all could have existed in classified form, while public astronomy struggled with conventional analysis methods. If so, the claimed ability to track 3i Atlas for 20 years becomes more plausible. You'd need advanced pattern recognition to distinguish it from background noise at enormous distances, but AI provides that capability. We're left with a picture of a universe more populated, more active, and more structured than most people realize. Gravitational waves revealing galactic-scale patterns, quantum sensors detecting faint signatures at solar system boundaries, plasma physics discovering new states of matter, AI finding anomalies humans missed, and at the center of this emerging picture, an object that arrived exactly when decades of preparation suggested it would. There's one more piece, one final revelation from December 2025 that ties everything together in a way that feels almost too perfect. Part 15, the December 2025 Solar Wall. Revelation. The sun creates a bubble. Solar wind, the stream of charged particles flowing outward from the sun at hundreds of kilometers per second, pushes against interstellar space, carving out a region called the heliosphere. The boundary where solar wind pressure balances interstellar pressure is the heliopause. We've known this conceptually for decades. Voyager 1 crossed it in 2012, Voyager 2 in 2018. We have direct measurements from inside and outside the boundary. What we didn't have until December 2025 was detailed imagery of the boundary structure. NASA released updated heliosphere boundary maps based on data from multiple spacecraft, ground-based observations, and new modelling techniques. The surprise wasn't that the boundary exists. The surprise was how sharp it is, how structured. Previous models predicted a gradual transition, a broad region where solar and interstellar plasmas mix turbulently. The new data shows something different. The boundary is thin, organised, almost architectonic in appearance. Not literally architectural, not built by anyone, but possessing geometric regularity that seems unlikely for a purely natural boundary between fluid flows. The boundary exhibits preferential directions, regions where it's stronger or more clearly defined. These directions correlate with the galactic magnetic field orientation, which makes sense. Magnetic fields shape plasma flow, but they also correlate with the trajectories of known interstellar objects. 3i Atlas entered through a region where the boundary shows enhanced definition, where the transition from solar to interstellar conditions is particularly abrupt. So did Oumuamua, so do several of the AI-flagged anomalous objects. Why a sharp boundary matters is subtle. It suggests the heliopause isn't just a pressure balance, but a functional membrane, a barrier that particles must cross rather than smoothly transitioning through. Particles crossing barriers behave differently than particles transitioning gradually. They can be organised, filtered, sorted by properties like charge or mass. You could think of the heliopause as a filter for interstellar material, though that anthropomorphizes a natural structure. But if the boundary filters, it could also interact with objects crossing it in ways that impart structure. An object entering from interstellar space would hit this boundary travelling at high velocity. The shock of transition could organise plasma around the object, could create the layered shells we observe around 3i Atlas. Natural processes at boundaries create structure all the time. Bow shocks around planets, shock fronts from supernova explosions, even water flowing past obstacles creates organised turbulence patterns. The speculative interpretation goes further. If the heliopause is organised, sharp, structured in ways that seem unlikely for random plasma flow, maybe it's not entirely natural. Maybe it's shaped by something, stabilised deliberately to serve a purpose. That purpose could be protective, shielding the inner solar system from harsh interstellar radiation, or it could be instrumental, creating conditions that affect how objects cross the boundary, perhaps making them visible to sensors positioned to watch. This ventures into territory where science and speculation blur. We have data showing unexpected structure. We can offer natural explanations invoking magnetic field geometry and plasma physics. Or we can offer speculative explanations invoking intent. Choosing between them isn't possible with current evidence. Both fit what we observe. But the pattern throughout everything we've examined is structure where chaos was expected. Organised plasma around 3i Atlas, geometric emission patterns, classified surveillance networks built on 20-year predictions, AI discovering regular anomalies in archived data, gravitational wave background showing directional concentrations, and now the heliosphere boundary, the wall between us and the galaxy, showing organisation that seems too perfect to be coincidental. If the Sun has a wall, if something outside that wall sends structured anomalous objects inward, following trajectories that correlate with the wall's geometry, if surveillance systems existed for decades to watch for these arrivals, if academic papers from 20 years ago predicted the exact technologies needed to detect and study them, what is the real story of 3i Atlas? We don't know. That's the honest answer. We have pieces of a puzzle. Some pieces fit together clearly. Others might belong to different puzzles entirely. The leaked files might be authentic documentation of classified programs, or they might be elaborate fabrications. The Cassandra paper might represent visionary academic work, or it might document preparation for predicted events. 3i Atlas might be a natural interstellar comet, exhibiting rare but explicable behaviour, or it might be something else. What we can say with confidence is that the patterns are real. The infrastructure described in the leaks corresponds to capabilities that would be necessary to detect and study objects like 3i Atlas from extreme distances over extended periods. The timeline works if you assume decades of preparation. The technologies exist. The physics allows it. Whether it actually happened remains unproven. The unanswered mystery persists because the evidence is simultaneously compelling and inconclusive. We have enough to ask profound questions. We don't have enough to answer them definitively. Maybe that's intentional. Maybe the leaks were designed to raise questions without providing conclusions, to shift public discourse while maintaining deniability. Or maybe we're witnessing the emergence of information that was never meant to be public, information that challenges our understanding of our place in the galaxy. 3i Atlas continues its outbound journey. It's past perihelion now, heading back toward interstellar space, growing fainter as it recedes from the Sun. Ground-based telescopes track it when possible, though opportunities diminish as it fades from view. If the leaked Oracle 6 platform exists, it's presumably still watching, gathering data until the object crosses the heliopause and vanishes into the darkness between stars. What happens next depends on what 3i Atlas actually is. If it's natural, it becomes another data point in our growing catalogue of interstellar visitors, unusual perhaps, but ultimately understandable within known physics. If it's something else, if it's a marker or beacon or probe, its departure might trigger events we can't anticipate, or nothing might happen. The object might simply fade away, leaving us with questions and incomplete evidence, forever uncertain whether we witnessed something extraordinary or merely projected our hopes and fears onto a chunk of ice and rock that happened to behave strangely. The greatest mysteries are the ones we can't fully solve. They haunt us. They inspire new questions, new observations, new theories. 3i Atlas has joined that category, whether it deserves to or not. we'll be analysing its data, debating its nature, and watching the skies for similar objects for decades to come. And maybe that's the point. Maybe the real revelation isn't about this specific object, but about what it's taught us to look for, how it's changed our perspective on what might exist in the universe beyond our small corner of space. The leaked documents, authentic or fabricated, have forced us to confront possibilities we previously dismissed. The Cassandra paper, visionary or preparatory, demonstrated that someone 20 years ago imagined a future that looks remarkably like our present. And 3i Atlas itself, natural or artificial, has shown us that the universe still holds surprises, that our models and theories remain incomplete, that we're still learning what's possible in this strange, vast cosmos we inhabit. The story isn't over. It might never be over. But that's appropriate for a mystery this profound. Some questions aren't meant to have final answers. They're meant to keep us looking up, wondering, searching, hoping that someday we'll understand. Until then, we have the data, the patterns, the implications, and the haunting possibility that we're not alone in recognising what just passed through our solar system.